Hi, welcome to Solideo Gloria Physical Chemistry. Today's topic is about molecular symmetry. In particular, we are going to talk about application of symmetry. In this case, we are going to apply group theory based on molecular symmetry. So there are many applications possible, but we are going to concentrate on symmetry orbitals or symmetry adapted molecular orbitals and molecular vibration, and determine if a certain vibration is IR infrared spectroscopy, IR active, and or Raman active. So let's begin. Let me get the laser pointer. So this is the listing of what we can do with the group theory. So predicting the polarity of molecule. If a molecule is a molecule a polar or non-polar, just like that. So a molecule have a permanent dipole moment, that's polar molecule. And if it belongs to point group CN, CS, and CNV, if it belongs to this, then it has a permanent dipole moment. So, and also, a molecule cannot be a permanent dipole, cannot have a permanent dipole moment if it is it has a center of inversion, so asymmetry, or belong to D point group, D6H for benzene, like that, and also belong to TOR or cubic group. So this, if we have symmetry elements known for the particular molecule, actually we can see the shape of the molecule and can determine this quite easily. But based on the symmetry element that belong to the molecule, then we can determine if that's polar or non-polar based on these criteria. And also, and chirality can be also determined. Optical activity also can be determined based on the symmetry or group. Chiral molecule must not have improper axis of rotation, SN, and also inversion symmetry or mirror plane, then that could not have optical activity. And also, third thing we can think of is that in atom itself, we can have so-called hybrid atomic orbital. In that case, we can choose atomic orbit, individual atomic orbital, make a mix and to generate hybrid orbital. In that case, we can mix only those which belongs to same symmetry. So predicting orbital used in sigma bond, sigma frame, and group theory can be used to predict which orbitals of a central atom can be mixed to create hybrid orbital. So that's one. These three application could be done. I mean, it's done intuitively. And we are going to concentrate on these two topics. So first one is the molecular orbital. So this is the question is the which molecular atomic orbitals to be combined to generate the molecular orbital. So molecular orbital results from combining or overlap of atomic orbitals, and then we have to choose atomic orbitals with the same symmetries so that it can represent molecular orbital properly, symmetry adapted molecular orbital. I'm sorry, symmetry adapted linear combination of atomic orbitals. That is the proper molecular orbital. Okay, so this is the first topic we are going to talk about, and then determine the symmetry property of the molecular vibration. Rotation, translate, any motion actually, not only the vibration. So determine symmetry property of molecular motion, including translational, rotational, and vibrational. And then group theory can be used to predict which molecular vibration is of the molecular motion, and then can also determine if that vibration is active in infrared spectroscopy or active in Raman spectroscopy. So those are the application, and then here is why. Well, molecular Hamiltonian and also the potential field are invariant about molecular symmetry operation. And the wave function itself is a probability amplitude, and the square of the wave function is the probability of electron distribution. So wave function must be eigenfunctions of the symmetry operation, meaning is that if symmetry operator operate to the square of the molecular wave function, it leaves it invariant. It doesn't change, which means that if the symmetry operator operates on a wave function, molecular wave function, it could be symmetric or anti-symmetric. So molecular orbital product or total wave function of a molecule is a product of molecular orbitals, occupied molecular orbitals, of course. So each molecular orbital must have the same symmetry as the molecule itself. So we have to construct molecular orbital according to the symmetry of the point group of the molecule. That's basically what we have to do when we generate molecular orbital out of atomic orbitals. What is behind or base? What is the basis of this? Is that we firstly molecular orbital is generated by linear combination of atomic orbitals. That's the way we do quantum chemistry calculation, quantum mechanical calculation. So what combination is kind of right? That's the question here. So symmetry adapted linear combination of atomic orbitals will generate proper molecular orbital. That's the same. That's the theme here. Okay, so now our kind of beloved example, water molecule here, and then the configuration of electrons of the water molecular orbital is just this: 1a1, 2, 1a. It's just like 1s2, 2s2, 2px2, 2py2, 2pg2, something like that. Just similar to that: 1a1, 2, 1a1, 2a1, 2, 1b2, 2, 3a1, 2, 1b1, 2, that's like this, and then we represent this electronic configuration of the water molecule as 1a1. Okay, so the question is how you make this one. And when you read the article, especially for small molecules, they describe the molecule with this kind of molecular orbital symbol. So here I will explain how you can generate this symbol for the molecular orbital. So let's go back to what symmetry group water belongs to, which is C2V, and then class or element of the symmetry elements are E, C2, sigma V, and sigma V prime symmetry. And then there, for these molecules, irreducible representations are A1, A2, B1, B2. Let me give you a little bit of detail. Last time, I probably just skipped it. The Mulliken symbol. Mulliken symbol is such a way designated such a way that for C2 or CN rotation, if that is symmetric, that's 1. Antisymmetric, -1, right? And if there's sigma V plane, if that's symmetric, that's 1. I'm sorry. If symmetric, for C2 operation, CN operation, if symmetric, that's A. If not, antisymmetric, then that's B. So C2 operation, A1, A2 operations are all 1, that's symmetric. B1, B2 operations are antisymmetric, so -1 is here. And sigma V case, symmetric 1, antisymmetric -1. So A1 symmetric, B1 symmetric, A2 antisymmetric, B2 antisymmetric. Sigma V case probably we just use C2 and sigma V for A1, A2, B1, B2. We don't use this one. And did I say, yeah, we covered this one before in the previous lecture. So the coordinate X and Y and Z behave just like A1 irreducible, in this case, for C2 symmetric group, Z, X square, Y square, Z square, all behaves just like A1 irreducible representation in terms of the symmetry, and XY according to A2, X and XG, B1, Y and YZ behave just like B2 symmetry operation. Okay, so this is the character table we are going to use. And then one thing more here, for a central atom oxygen in this case, there are orbitals like 1s orbital, 2s orbital, 2px, 2py, 2pz orbitals are all occupied, or more or less occupied. So it has 8 electrons, so 1, 2, 3, 4 orbitals might be occupied, or combination of it is occupied. Well, 1, 2, 2, 2, 1, 1 is kind of thing we kind of represent or kind of denote the electron configuration of the oxygen atom in general chemistry. But this 1s orbital, 1s H1, HA, 1s HB orbital, as itself, it is not a symmetry. It is not symmetric at all, or antisymmetric either. So that we need to make a linear combination, because 1s A, 1s B, if you rotate it, it just exchange, but it does not representing what it is in terms of symmetry. So we have a combination 1s HA plus 1s HB, chi1, 1s HA minus 1s HB, chi2. Chi1 is symmetric for C2 rotation. Yeah, we just exchange, but still the same. Chi2 is not symmetric. Chi2 is antisymmetric with respect to C2 rotation. So that is why here chi1 is 1, chi2 is minus 1 here, just like this. So each orbital, 1s orbital, 2s orbital, 2px, 2py, 2pg, chi1, chi2, just like this combination, orbitals for this E, C2, sigma V, sigma V prime could be obtained in these representation. And then we can identify, for example, 1s and 2s orbitals of oxygen atom does not change. So all are symmetric. In this case, they are totally symmetric. So they are totally symmetric. Irreducible representation, which is A1. So this orbitals is called A1 orbital. So this is atomic orbital, and then has the symbol like this. 2px orbital is this one, actually placed on, probably projected on to the x-axis, so it must behave as A2. 2px, A2. It's 2px. B1, I'm sorry, not here. X is here, B1. So that's B1. Actually, what you do is that if you operate to this 2px orbital, E operation leaves it unchanged, so symmetric. C2 rotation is x to the minus x, so antisymmetric. Sigma B is xg plane, so it doesn't change. So 1. Sigma V prime is that YZ plane, so about x1 is kind of a reflected plus lobe to minus lobe, so minus 1, so antisymmetric. So this is the same as B1 representation, so the symmetry of the 2px orbital is B1. Okay, that's how it works. So 2py B2, just like here, Y here, and also 2pz, Z is here, and A1 again. And also for this E operation leaves it unchanged, C2 operation leaves unchanged, and then sigma v unchanged, sigma v prime unchanged. So this is also totally symmetric A1. X2 is different. E leaves it alone, so doesn't change, symmetric. Sigma v prime is in the same plane, so it doesn't change. So 1 and 1 here, and then C2 flip the sign, sigma v flip the sign, so -1 -1. This is just here in B2, so that's B2 symmetry. So each atomic orbitals in the central atoms oxygen and linear combination this way or other way, chi1, chi2 of hydrogen atomic orbitals have this A1 and B2 symmetry. Now we do linear combination of this. This is kind of a combination of atomic orbitals, but make a combination of these atomic orbitals to generate a molecular orbital, linear combination of atomic orbitals. And then the rule of thumb is that we combine, so-called mix the atomic orbitals with a similar energy or the same energy. So in this case, 1s orbitals is far lower than S2 or 2s or 2p orbitals, and that is non-bonding, and that does not mix with you can do that, but the mixing coefficient is negligibly small. So hydrogen orbitals. So A1 is non-bonding orbital, is inner orbital, co-orbital of the oxygen. And then you could obtain linear combination of S and A1 because this chi1 and 2px b1 it does not combine with either chi1 or chi2, because chi1 or chi2 is b1 and b2. So b1 must be just non-bonding. 2px is non-bonding, and then 2py b2 or symmetry, and it can combine with chi2. Okay, and again 2pg is A1 equal to combine with chi1. So linear combination either with 2s or 2pg or 2py. So 1s orbital and 2px orbital is non-bonding, and 2s orbital plus oxygen 2s, and chi1 is bonding. 2pg orbital plus chi1 is bonding. Okay, 2py plus chi2 is bonding. 2pg minus chi1 anti-bonding, because that's anti-bonding character. 2py minus chi2 is anti-bonding. So we gather from lowest energy to higher energy is x 1s orbital, oxygen 1s, and this bonding, that bonding, and again bonding, and then non-bonding orbital, just like that. Yeah, then anti-bonding orbital. That's the kind of order. So when we order that, so we first, there are how many A1 orbitals? A1. Yeah. So there are 4 A1 orbitals. So from the low energy to among the A1 orbitals, we put the order number 1, 2, 3, 4. And how many B1 orbitals? There are just one B1, so just one B1. And there are 2 B2 orbitals, so 1 and 2 B2 orbitals. So in terms of increasing energy, 1A1 and 2A1, and that's bonding. And then 3A1, 1B2. 1B2 is lower, it's also bonding. And then 3A1, the reason is that P orbitals is this way and PG orbitals is that way, so it has less overlap, I guess. So so this is the order. So 1A1, 2A1, 1B2, 3A1, and then non-bonding 1B1. So this is the orbital order in energy. And then each orbital is doubly occupied. So 1A1, 2, 2A1, 2, 1B2, 2, 3A1, 2, 1B1, 2. So this is the electronic configuration of water molecule. So that's how we do symmetry adapted linear combination of atomic orbital generated proper symmetry adapted molecular orbital. So this is one application we could do. Okay. Then next topic is the molecular vibration. Okay, so it's a little bit hard topic, but let's do it a little bit carefully so that we understand this, and then when you read the journal or do molecular calculation and find or get the definite idea what normal mode, how normal mode works. Okay, and in general vibration, and also you can further apply this to designate which molecular vibration correspond to which peak in either infrared or Raman spectra. Okay, key question is how many vibrational mode belongs to each irreducible representation. Okay, so we'll find out. So molecular motion should be invariant under symmetry operation. Basically, it does not. It should. It must. If symmetry-wise concerned, molecular motion does not change the symmetry. So molecular motion should be invariant under symmetry operation. That belongs to, of course, the point group of the molecule. And how we find out how many vibrations of molecule or vibration or any molecular motion belong to each irreducible representation is that we make a translational vector. Meaning is that each atom has middle x and y and z directional motion. Okay, so that we call translational vector of the atom, and use that as the basis, and then find out the irreducible representation of the motion. There are three kinds of motion: translational, rotational, and vibrational. So rotational and translational motions removed from the set of molecular motion. What left are vibrational motion, and then each vibrational motion, I would say vibrational mode, could be assigned to a symmetry representation, irreducible representation of the point group. So each set of each different symmetry. So how we do that? Only a vector that are either unchanged or have become negative of themselves by symmetry operation could contribute to a character. What it means? So if you operate the symmetry element, so symmetry operation to the molecule, if a atom does not move or does not change for that operation, then it is possible to contribute to the character. So that atom has x and y and z coordinate. So if that one of the coordinate does not change, that's +1. It doesn't change, that's symmetric. And if it flip the sign, then it make a negative contribution. So for example, C2 rotation, it change if that's z-axis rotation, g coordinate doesn't change, but x and y coordinates flip the sign. So minus minus plus, so totally -1. So -1 is the contribution for that operation for the atom that does not move for the operation. We'll find out, we'll check out what these mean with the example. Okay, so only the vector that are either unchanged or have become negative of themselves by symmetry operation contribute to the vector. So the rule of thumb is that a vector is unchanged or become the negative of itself if the atom are not moved. Okay, first condition is that atom must not move for the operation. A reflection case, we leave two vectors unchanged and others change its sign. So contribute, 2 does not change, 2 don't change, and 1 change. So +1 +1 -1 is +1. Okay, and rotation, just I explained with C2 rotation, leaving the position of atom changed will invert the direction of two vectors and then leave one unchanged. So +1, -1, -1, -1. That's the contribution. So E operation, this identity operation is that it doesn't change any position of the atom nor the direction of the translational vector. So each atom contributes 3. And sigma is a reflection. If a atom does not move for the reflection operation, and it can contribute, but two coordinate does not change. One coordinate changes sign, so it contribute +1, +1, -1 is +1 contribution. C2 operation, just like as I said, -1. And inversion, in terms of inversion, all coordinates, 3 coordinate changes sign, so -3. And C3 operation, if the C3 operation, if it doesn't change, but the contribution is 0, because there is a way you can find out. Okay, so let's just accept it, because it will complicate the lecture, but that's it. And so each symmetry operation, the number of atoms unchanged in its position times this, okay, this contribution, that's the character for the symmetry operation. Okay, and then that's the reducible, that makes the reducible representation, and then we can decompose that reducible representation into irreducible representation. That will give you what kind of molecular motions there. Okay, let's do some example and you will find out what it is. Okay, so our example, very familiar example, which is water molecule. So X, Y, and Z here are translational vector for oxygen, hydrogen, and the other hydrogen. So there are 9 possibility to change or unchange or whatever, the flip the sign, just like that. Okay, so character contribution for E, there are 4 symmetry operations for C2V group. Okay, for E, C2, sigma V, sigma prime, and E operation, each atom which does not move contributes 3. Because if this atom E operation, this does not move, so also X and Y and Z translational vector does not change its direction, so contributes 3. Also that contributes 3, that contributes 3, something like that. And also C2 operation. In this case, C2 operation, H and H change the sign, and actually one atom does not change, and then X and Y change the sign, Z does not. So in that case, -1 is the contribution. Sigma B, you remember that sigma B is this kind of bisecting plane, and then this changes, this one goes to that, and that hydrogen goes that, so they don't count, but oxygen itself does not change. So in the case, G does not change, and also Y does not change, but X does. So +1, +1, -1 is +1, just like that. And sigma V prime is just this total, I mean the molecular plane, yeah, molecular plane. So in that case, Y and Z does not, I'm sorry, X and Z does not change, but Y changes. So 2 does not change, 1 changes, so +1. So that's the contribution, okay? Okay, so number of fixed atoms for E operation 3, C2 operation 1, right? This changes position. And sigma V operation just 1. And also sigma V prime 3. So contribution 3 for each atom which does not change its position. So 3 atoms, 3 times 3 is 9. Now -1 times 1 -1, 1 times 1 is 1, 1 times 3 is 3. So this is the kind of character contributions for the molecular motion. So reducible representation is 9, -1, -1, 3. So in that case, it's just this. Then how this gamma is 9, -1, -1, 3. This is a kind of a quadruple vector, something like that. And then we can decompose gamma into A1, A2, B1, B2. How we do that is that you just project this vector into this and then get the contribution. And exactly how you do that is that make a dot product. Okay, 9 times 1 plus -1 times 1 plus 1 times 1 plus 3 times 1, which is what you get is 12, right? Yeah, 12. Yeah, 12, 12. And then what is H? H is the total number of symmetry element here, which is 4. So 12 divided by 4 is 3. So that's why you get 3 here, which means that this gamma representation has 3 A1 representation, A1 irreducible representation. And then A2 case you do 9 times 1, -1 times 1, 1 times -1, 3 times -1, which is 4. And then 4 divided by 4 is 1. So you have 1 A2. And now 1 times 9, -1 times -1, 1 times 1, -3, -1 times 3. So which is 8 divided by 4 is 2. So B1, B2 case you can get also 9 plus 1, -1, 3 plus 3, 12. 12 divided by 4 is 3. So 3, 1, 2, 1 contribution for irreducible representation. So gamma itself is 3A1 plus A2 plus 2B1 plus 3B2, just like this. So this is the kind of a total representation gamma for the molecular motion. Now you can decompose or convolute, I would say, decompose this into molecular translation, rotation, and vibration. How we do that? From the character table. You see, in the character table, there are the molecule with this symmetry or the symmetry group has this rotation x and y and z that behaves just like A2 irreducible representation and B1 representation. Rx is rotation x-axis, rotation is B2 representation, and x and y and z coordinate also A1, B1, B2, A1 representations respectively, and then x square, y square, and these are just a kind of character table will give you the idea. So here, now what you have is that translational motion. So translational motion's case, all x and y and z are contributing. So translational motions are, well, x direction, y direction, z direction. So A1 plus B1 plus B2, A1 plus B1 plus B2 are translational motion, or representation for the translation motion is decomposed or it is composed of A1, B1, B2 irreducible representation, and rotations here A2, B1, B2. Okay, H2O, there are 3 atoms, so 3 times 3, 3n, 9 total degrees of freedom, and 3 of them are translational, and another 3 of them are rotation. So 6 motions are translation and rotational motions. So now you subtract these translation and rotation from the total gamma, minus gamma translation, minus gamma rotation, will leave you here. Subtract 1A1, then 2A1, and then 1A2 is gone, 2B1 is gone, and then 3B2 minus B2 minus B2, 1B2. Okay, so this is 2A1 plus B2 is the vibrational representation. So vibrational representation has this kind of 2A1 plus B2. Then we can further decompose into normal mode. We call it normal mode. So you will see how it works. So vibration has 2A1 plus 2B2. So A1 is totally symmetric and B2 is antisymmetric against C2 rotation and antisymmetric against sigma V sigma V reflection, and symmetric against sigma V prime reflection. So firstly, A1 is the A1 symmetric. So A1 symmetric is in such a way that totally symmetric means that it's okay. Firstly, the vibration does not change its center of mass. Okay, molecular center should not change. So if you put these all three vectors, it must be zero. It cancels, all of them cancels totally. And also symmetric stretch is that these all three vectors are A1 E operation leaves it, so just one, that doesn't change. And then C2 rotation will just change, and sigma V and sigma V prime also. So these two you can draw just like that. So first one is A1 stretch, symmetric stretch, A1 bending. Okay, so this is it. And okay, that's it. And asymmetric stretch is this one. So this one is that basically this also based on this symmetry operation. You could identify this as a B2 motion. So two A1 motions and one B2 motions are molecular mode or molecular vibrations over the water molecule. Okay, so this is kind of thing I just want to show you as a symmetric stretch. And well, this is a methylene group. So this yellow or kind of dark yellow is a carbon, and which kind of moves a little bit, but H is lighter and then it's exaggerated. The motion is exaggerated, but anyhow. So considering this slightly move, but you observe this motion. So symmetric stretch is just like this. Okay, just like this, yeah. And then antisymmetric is just like this, yeah. Scissoring is this, and then rocking, okay. And wagging is this, and then twisting is this, yeah, something like that. So this is kind of what you expect as those molecular vibrations and as normal mode. Well, actually, when you do quantum mechanical calculation, and then when you do Hessian calculation, the second derivative of a Hamiltonian, and then you can kind of transform into the normal mode. So make the Hessian leave only diagonalize the Hessian, and then that eigenvector will give you this molecular vibration for the normal mode. And also now, lastly, the final topic for that is that if you find that vibration and know which irreducible representation is for the vibration, and then you can determine if that vibrational mode is normal mode is active in IR spectrum or active in Raman spectrum, just like that. So molecular vibration to be active or seen in the infrared spectrum, it must change its dipole moment. So the dipole moment vector have this dipole moment is something times X coordinate or Y coordinate, Z coordinate. So if that vibration has component in X and Y and Z, meaning is, you see, remember that for the water molecule is either totally symmetric or B1 and B2, right? So that if those modes are infrared active in the case. And also the Raman spectrum is if the polarity changes, if the polarity is the X, the kind of product of coordinate X, Y, Y, Z, and XZ, X square, Y square, Z square. If these are the components in the vibration, that vibration is Raman active. That's the kind of criteria we are going to apply. So we obtain water molecule. Normal mode for the water molecule is either A1, or B2. So totally symmetric. So symmetric stretch or symmetric bending, and anti-symmetric stretch. Okay. So in this case, A1 has Z and X square, Y square, Z square, and there's B2. B2 is this one, and Y and YZ square. So either these two or that, symmetric stretch, symmetric bending, or anti-symmetric stretch. These all three modes here, X and or Z and Y here are all infrared active because it contains the Z and Y, and also all are Raman active because X square, Y square, Z square there, and YZ is included here. Okay, so either A1 and B2, actually A1 and B2 vibrations are both Raman and infrared active. So that's basically what we conclude about the molecular vibration. And we cover the three kind of in terms of vibration and then symmetry adapted molecular orbital, two actually topics in application of group theory or application of molecular symmetry. Thank you for your patience in this long lecture, but enjoy your molecular symmetry.